In this video, we describe some statements of Dalton's atomic theory. So Dalton's atomic theory follows naturally from the fundamental chemical laws that we have described in the prior video. Okay, so here are some of the statements of Dalton's atomic theory. First, an element is composed of atoms. Okay, so if you take, say, carbon, a pure element, you can actually think of an atom as the smallest piece of that piece of carbon, okay, that you can still call carbon. All right, so you can think in Dalton's world that you would slice that piece of carbon into small pieces, ever smaller pieces, until you get to a piece that is small enough that you can, or small enough that you cannot divide it anymore, but you can still call it carbon. Okay, so that's one of the statements of Dalton's atomic theory. Another statement is that elements differ in the atoms, right? So the atoms of carbon are going to be different from the atoms of iron in some fundamental way, which we still don't know at that particular time. Okay, but that's something quite important. Okay, when you have two different elements, they're both composed of atoms, but the atoms are different for each element in some fundamental way. Okay, now Dalton also attempted to explain the formation of compounds. Okay, so these are going to be substances that contain more than one element. Right, so for example, in water, you're going to have hydrogen and oxygen. Okay, so Dalton explains the formation of these substances, these compounds, by the combination of the atoms of those elements in some specific ways, which again, we still don't know how they are. Okay, so when we have a molecule of water, we know that that is the combination of atoms of hydrogen and atoms of oxygen, but we still don't know quite well how that combination works at the microscopic level. Okay? And finally, another statement of Dalton's atomic theory is that, well, chemical reactions, when two substances react to generate a couple of substances, okay, the only thing that really is taking place there is just the reorganization of the atoms in those substances. Okay, so to illustrate what a chemical reaction is, we can use a combustion process, okay, like the burning of methane. Okay, so you can get methane, burn it with oxygen to generate CO2 in water. Okay, balancing the reaction, we need a 2 there, we need a 2 here. Okay, so in Dalton's atomic theory, what we actually think is that methane is some substance that is composed of carbon and hydrogen. And again, the formula at that particular time was actually not known. They didn't know that methane was CH4, but they knew that there was some hydrogen, some carbon, and the relative masses of each of the elements in that compound. Okay, so when this substance, when this fuel reacts with oxygen, okay, that generates some products. And again, the mass has to be conserved. Okay, so that comes from the law of conservation of mass. Okay, and the only thing that actually happens is that the atoms are rearranged. Okay, here carbon is in a compound with hydrogen, here carbon is a compound with oxygen, and so forth. And again, so all of this can be explained appealing to the concept of an atom, and that's why we call this Dalton's atomic theory. Now, something that is quite interesting of Dalton's atomic theory is that with that theory alone, you actually cannot predict the formulas of compounds. Okay, so think about water. Dalton's time, actually, they didn't know if water, which is a compound of oxygen and hydrogen, they knew that. They didn't know if water was oxygen H, for example, or perhaps H2O, or perhaps HO2. They actually didn't know this. But what they did know was that the relative masses of oxygen and hydrogen in that water compound was A to 1. Okay? A to 1. Right, so the problem of determining the particular formula, knowing the relative masses of the elements in those compounds, is that they actually didn't know what the mass of a particular atom of a particular element is. Okay, so they didn't know that the mass of hydrogen was 1, they didn't know that the mass of oxygen was 16, and so forth. Okay, that came a little later. Okay, so actually they couldn't find out what of these two structures is corresponds to water. Okay, so for example, you can think that if the relative mass of oxygen to hydrogen in water is OH, and the formula is OH for water, then the atomic mass of oxygen would be 8, which is not correct, and the atomic mass of hydrogen would be 1. Okay, if you think that water is H2O, and instead you have an 8 to 1 ratio, then that would mean that the mass of oxygen should be 16, and the mass of each atom of hydrogen would be 1. In that case, you actually find out that the relationship between oxygen and hydrogen is still 8:1. Again, we actually know today that that's the one that takes place, the one that actually confirms the reality. But again, at the time of Dalton, that was not clear, okay, because they didn't have atomic masses. Okay, now moving towards the determination of the formula of compound and the determination of atomic masses, there were a couple of other theories of sets of experiments, okay, that were necessary in order to, again, nail down the fact that when you have water, this is H2O and not OH. Okay, and that was the work of Gay-Lussac and Avogadro. And these people were working with gases. Okay, so what Gay-Lussac did is actually study the formation of water to recognize the following. Okay, again, these were all experiments with gases, and that is very important. Okay, not liquids or solids, bad gases. Okay, so the idea of Gay-Lussac is that he was mixing these gases, and he was very carefully controlling the conditions of the gases, the volume of the containers of the gases, the pressure, the temperature, and he recognized that in order to generate water, okay, one volume of water, whatever that is, okay, he actually had to mix 2 volumes of hydrogen and 1 volume of oxygen. Okay, which was kind of interesting because this suggests that there's more, there's more atoms of hydrogen than oxygen in water. Okay, which is something that they wanted to know. All right, now something that before actually taking that step and concluding the relative abundance of atoms in water, okay, Avogadro actually thought about what the volume of a gas is. And what Avogadro thought is that, well, if the pressure and the temperature is the same, okay, and you have 2 different gases in the same volume, well, what's going to happen is that, well, the atoms in those gases are going to occupy a volume that is actually very, very small compared to the separation between 2 atoms in that volume. So essentially, what you actually have in that volume of gas is empty space, okay? And that means that if you have 2 volumes that are identical, you should have about exactly the same number of atoms. Okay, so in Avogadro's idea was that, well, if you have the same number of atoms in the same volume, then you can actually rephrase this expression simply as saying that you're going to have the 2 atoms of H are going to combine with 1 atom of oxygen to generate 1 molecule of water. And then what that means is that now you actually can say that the formula of water might be H2O. It could also be H4O2. Okay, because we actually know the ratio is still 2 atoms of hydrogen to 1 atom of oxygen. Okay, so that they didn't know that at that point, but what is obvious is that water cannot be OH, according to these 2 experiments. Right, so these experiments led to additional knowledge, and eventually atomic masses were able to be measured. And these again are kind of the initial steps into the chemical theory that we use today to understand matter. Okay, so in the next few videos, we're actually going to delve a little deeper into exactly what is an atom, this atom that Dalton figured out. Okay, what are the components of an atom and why that matters to chemistry.